The history of color is a great example of where art and science are intertwined.
Pigments are things that come from the earth. It could be a stone, it could be a plant, it could be a beetle, it could be lots of different things, right? This is something we briefly talked about last time. The question is how they are bound, how they're put together, and when they're used. So one thing that I'll just start off with is this sort of historic chronology. This is talking about what metals or minerals or plants or animals were used, and there are all of these different terms. There's different things like umbers or sepias, or I highlighted the word lapis lazuli. There are certain colors that were just really, really, really hard to find in nature. Specifically Egyptian blue, this other type of purple. Ultramarine was one that was really, really, really difficult to mine and find the lapis lazuli. In ancient Egypt, they didn't have access to any plants or stones or anything that made blue, so they made their own blue.
Egyptian blue is made in a furnace by mixing together sand, embalming salts, chalk, and copper baked at high temperatures for 10 hours. Then what comes out are these blue lumpy glass frit. It would then be ground up as pigment.
Blue, for the most part, sort of far and few between for years in art history. I'm not going to go much more in depth about the historic overview of what did not exist, but I want to switch to perception of what did exist. For years, it was really just about mixing the materials that you had. A lot of those don't last very long. They fade in the sun. This was one of the earliest sort of art manual books that Alberti wrote. This was 1435, which is basically 10 years after Brunelleschi started developing linear perspective. Alberti writes extensively about techniques in perspective in this book. This is the fun part of really what I want to start to point to, is that what raw materials you had, what access you had to materials, what limitations there were, and then also how this idea of theory slowly develops over what we know. So the irony here is that the four true colors, whatever that true means, so the real colors in this time that was broadly and widely used in the Renaissance, was this idea of the four true colors that were associated with classical elements. The elements that we knew were fire, air, water, and earth. So just think about, in terms of science, this was real. This were the elements that they were referencing. And this was how those colors reflected those true colors, right? Which is something interesting when you see a lot of Renaissance paintings. Those are basic primary colors: red, blue, not yellow, but green and gray. Atmospheric perspective, this is something else that, through perception of the way things are, help to understand and coordinate and organize color. There was no real manual. That manual was the one I just pointed to that Alberti wrote. But one of the things that Leonardo was pointing to was the fact that observationally, things that are further away are grayer, things that are closer are going to have more contrast, things that are closer are going to be warmer, things that are further away are going to be cooler, right? It's a simple system that he established in his writings, atmospheric perspective. And this is the age of the Enlightenment, where there was a need for, a desire for an investigation, a deeper investigation.
That deeper investigation of color didn't come until about 200 years later, when Sir Isaac Newton wrote Optics, specifically asking the question, why is it when you shine sunlight through a prism, it splits into all of the colors of the rainbow? The common explanation was that there were impurities in the prism, hence appearance of colors would be there. Newton thought that the colors were already present in the white sunlight and tested his hypothesis. First, he made a rainbow by shining white light through a prism, then isolated a particular color of light with a slit in that rainbow. Then, he sent that color into a second prism. The deflection of the colored light did not change, implying that the colors themselves are pure. Newton concluded that the individual colors of the rainbow are the basic building blocks of white light.
Then what came from that was breaking down or understanding what I call the Roy G. Biv, the colors of the rainbow, and how that can be separated and defined in optics that he wrote. But then that goes a little bit further with Goethe, who was primarily a writer, but also did a lot of science, did a lot of art, among other things. One of the things that he's really famous for was traveling. And he was coming from Weimar, Germany, and would go down to Italy and spend time there. And crossing over the Alps, you have white-capped mountains. And he was doing all these little watercolors of the drawings, knowing what Newton had already been doing and understanding light. But there was this other thing that he developed, what's called a local color. Red apple, it's red. Okay, there's an orange, and it's orange, right? So you know the color of that object, you can name it. But there's more to it than that. There is what is reflected color. So colors that blend, that makes things appear differently. So for example, when I'm looking at that red apple, I might notice that there's some aspects of it that are going to be some purple areas, or maybe some orange areas, or some shadowed areas that might have tones of green in them, other things. And I'm not just talking about the surface. It has more to do with what is reflected or coming into your eye. One of the things that he realized that through was watching these white snow tops as the day moved, that you saw the light shifting on the colors that were there. The colors changed in the afternoon because the light changed, right? So that was one of the things that happened with Goethe that was a big step forward into understanding not just the physics of light and how it was refracted, but how it was also impacting what we see, our perception, based on what is reflected into our eye. So that went a step further with Philip Otto-Runge, which just oftentimes referred to as Otto-Runge. He basically took what Newton used a version of a color wheel, but treating it more like a sphere because it has certain dimensions to this idea of reflected light that we see. So that means we have to be mindful of looking at the upper part where there are lighter colors, so tints of colors, and then where there's the bottom of it, there is going to be darker colors, and how that impacts the visual weight of something, maybe the time of day, or the way things are reflected. So this is something that he is known for in the development of color theory. Moving forward, you had other people that started making discoveries. So there were certain properties that color had, and a big one Cheval made was when you put two bright colors next to one another, it creates a degree of contrast that just a light color or non-color next to another hue might not do. So you see that with the purple against the yellow versus the gray. What happens when you put a blue square on a brown, orange, dark orange background versus here where you put that orange, it's creating a different type of relative space and tension and contrast, right? Which was something that they were really interested in terms of art, when you can create areas of contrast, not just black on white, but how you can use simultaneous contrast. The next one, this is where we move back into physics. Helmholtz was looking at these trichromatic color theory, which is based on the primary hues that we were aware of, reds, greens, and blues. We see these wavelengths as the cones in your eyes. They are intensified by this division of what the wavelength is. The longer the wavelength, the less is coming in. Now, one of the things that Helmholtz did wrong was it was initially thought that they were even. It took some time to realize that the wavelengths were different.
The wavelength and frequency of light determines a hue, and the amplitude determines its intensity or brightness. For instance, a short wave has a high frequency. Our eyes register short wavelengths as high frequencies being bluish colors, while we see long frequencies as being a reddish hue. We register the brightness of a color or amount of energy in a given light wave as the greater amplitude means higher intensity, which means brighter.
This is what you see on your computer screens. This is what you see on your televisions. This is what's in a pixel. So a pixel is basically lots and lots and lots and lots of red, green, and blue. Now, the intensity of how bright one is, or the amount of red versus the amount of green, is going to create whatever that hue is. That's the way additive color creates the screens that you look at. This, I think, is fun for a couple of reasons. One is this, the wavelengths, you see that here, how that's broken down based on the low frequency and high frequency, that you see the low frequency colors are like red versus blue is going to be a higher frequency, right? The connection between the cones in your eye and your brain is seeing color. Magenta is not on the rainbow because it is a secondary additive color. CMYK, CM, magenta, cyan, magenta, yellow, and black. Magenta is not even on the rainbow. It's not in the Roy G. Biv. The way that you get magenta is by mixing blue and red. So what you're actually seeing when you see magenta is this combination of those two of wavelengths from both ends of the spectrum, the high frequency and low frequency. Here's a little fun experiment. Looking at the dot in the middle of the screen, 1 minute. This is what's called an after image. An after image is, it's when your eye is exhausted, the cones are exhausted from seeing the yellow, and what it's doing is it's producing the opposite of yellow, which is purple. But moving forward through the history of color theory, this idea of creating color space. So this was similar to this color sphere that we were talking about earlier, but there's a more systematic separation of what was then taking a step into looking for harmonies between colors where you see progressions in them. You see the values of dark to light and this idea of creating color spaces. Similar to what we were just doing with this after image looking, you have people like Rude, who was interested in this idea of luminosity, of how the chromatics, how bright a color is, and what makes a color bright. It has a lot to do with how, for example, much brighter a yellow would be than, for example, a dark blue is going to be toned down. So that's something that he was investigating, was the chroma, this how intense a hue would be, how bright it would be. Also, in the mid-19th century, you had the Weber-Fechner law. Now, Weber-Fechner, this is used in a lot of things, from sound to counting to other things, but it's also used in color. And the way this works is, if the physical fact of what you see, think of it this way, you go to Home Depot, you're gonna paint a wall in your apartment, and you see all these little color swatches, and you pick up the blue one, and you see on that blue swatch, there's like, maybe one's darker, maybe one's lighter, right? That's the physical reality of what you see. The psychological effect of this, meaning if they were actually small steps, it plateaus out. Let me explain that a little bit different, what I mean. This would be the physical fact of seeing those steps. This is what you think you see, but this is the reality of what is happening. Where if I have my palette and I'm mixing blue with white, I will need to double the amount of white to see one step. I'm going to need to double that again, twice as much more white to make the next logical step. And I'm going to need to double that again to get the next logical step. So this is something that has a lot to do with this magnitude. It's at some point where visually we just get exhausted with what we're seeing to be able to see the difference. Even if you're doubling a number, you're not seeing a significant shift. So another one of these sort of, in my opinion, fun effects that happened about the same time is the Bezold effect. Again, 1874, we're talking the end of the 19th century. And it's really a quite simple thing. you're having the same red bands that go through, but look at how significantly that impacts this field of red when that same field of red is on a black background, right? So the better example is the brick wall. You create a brick wall with white mortar, it looks different than if you create that same red bricks with black mortar. Completely different effect. This was used, and this was really significant for things at that time, which was everything from printing wallpaper or fabric production, creating dyes, because you were able to produce a broader range of products with fewer colors if you knew how to mix them well. So they look very, very different, don't they? In this one, the yellow strips are what go through, the blue do not. And in this one, the blue stripes go through, but the yellow does not. It's a really simple effect, but that's the way we see. That has everything to do with our perception. So moving forward towards the end of or entering the 20th century, this is still used. Liquitex paints will have that on the back of them. It will have the Munsell number, right? Because what it's doing is basically taking all of this system of the spheres that we were just talking about, and it's breaking them down a little bit more. But basically, it's the scale of black to white, so white being 10, absolute black being 0, and then that creating a gray tone, and then the chroma is how bright it is. The brightest that hue would go, and the value is the darker value, the higher value, and of course, you're going around are the different hues. And then as you move from this gray out slowly, it's getting brighter and brighter and brighter. As you go down a rung, it's doing the same thing, but it's a darker tone. Or if you're going up, it's a lighter tint. Okay, but it all ultimately comes down to hue, saturation, value. So again, this is important to mention this, that color and hue, the words in English are interchangeable, not all the time, but basically when I refer to a hue, it means a color, versus when you go to that Home Depot, they usually have fancy names like sea mist in the spring. Those are not real colors. Like the hue that's one of the things that I like about this chart, the colors that you would see on, for example, a Munsell scale. Red, green, and blue. Put them together, you get white light. Versus you put all of those colors together, and you get mud, or black. The primaries here, which we all know since like first grade, which is red, yellow, and blue. So let's talk about CMYK a little bit. So this is a printing system that was developed with the introduction of 4-color process inks. And what was also really important was it was wet on wet, which for painters, there's a huge difference between when you paint wet on wet versus when you paint even wet on dry or something else. It's just the way that the absorption works, and it does something different in the way that it reacts. If you have an image, is that you see the separation of 4 images. This is this idea of a 4-color separation. So you have the cyan at the top, the magenta, the yellow. You put them all together, and you get that bigger image. So this is the way it's actually working, that you have these individual dots. Here you see a zoom in a little bit more. Up there where you can see what is called half toning, where you're putting a dot on top of a dot, and it basically is the amount of one of those 4 colors that's going to dictate what color you're going to get. But this is Seurat and pointillism. 20 years earlier, it's what you might even call like stippling, dot, 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 dot. And when you zoom in, you can see that each individual area where there's maybe more blue, there's going to be more blue dots and more yellow dots. Only colors that can't be created are red, yellow, and blue, meaning you can't mix them. You can't get them by mixing other colors. You got the primaries, the secondaries, and a lot of people are not familiar with what is the tertiary colors, which is basically the colors in between. But we're going to start with value, where you have basically the color plus white is a tint, color plus a gray, which is a tone, and then you have color plus black is a shade. Now, this is how this works. I'm sure some of you, if you're ever using an Adobe product, this is basically how it works. You have your saturation that goes in this direction, so basically brightest is going to be up here, and then your value, your whitest, is going to be here. Well, this is basically what was developed by Munsell. Here's another guy. So now we're moving into the 20th century finally of color theory, but this is a little bit more practical use. So this is Johannes Itten, who is one of the teachers at the Bauhaus. He developed this idea of the color star, which is really just a combination of a lot of the things that we've already been talking about, but it's a little bit more concise. He started talking about harmonies, which no one else was really doing up until then. If you look at the red more carefully, and you compare it then to, you go back and forth and look at the blue, you'll realize that it sort of appears that the blue is like a hole, like a tunnel, like really, really far away, whereas the red appears to come forward, which it's not something that's measurable like science. We see how some artists use that. This is Rothko. Artists will play with space and light, and specifically people like Rothko was a color field painter in the 1950s. This idea of perception and color is dependent on light, and it changes as the day. And that's one of the things that's fantastic about a lot of the Rothkos, because it appears to be different types of sunsets or sunrises or different times of the day or different landscapes. Joseph Albers said, in visual perception, a color is almost never seen as it really is, as it physically is, right? This is the comparison that I want to make. Unlike science, art is not measurable because the fact makes color the most relative medium. So relativity means this idea that it's going to change. It's not going to be a constant, which constants are things we like in science, but we don't have them in art. So he wrote a book called The Interaction of Color in 1963, and this is really one of the staples for color theory. He was from Germany, studied in the Bauhaus. The Bauhaus, if you don't know, was an art school. It was really one of the first, that's why I call it the OG art school. It was primarily architects and designers and artists, and a lot of very, very well-known artists were teaching there. The Nazis, they came and basically said, you guys are really bad people for all of this really advanced stuff that you're all doing, and you're not allowed to do this here anymore. So they shut down the Bauhaus. And when they did that, a lot of people left Germany in the 1930s, and Joseph Albers came to America. And he first started teaching at a school called the Black Mountain School, which was very significant because a lot of his students were very famous then. Robert Rauschenberg, if you know any of these names, very well-known neo-Dada artist, pre-pop, proto-pop artist, and Cy Twombly. Merce Cunningham is a very, very famous dancer. So a lot of very influential people from the 1950s and 1960s. And then after that, in the 1960s, he was the department chair of design in Yale. That's when he started working with the majority of his color theory experiments with his students there, which led to his book, The Interaction of Color. This is what he's most well known for in his own work. Very, very simple, very, very minimal, very, very Bauhaus. So you stare at this, what do you see? You see this kind of weird brown, this kind of bright yellow. Would you say that these two colors are similar or different? Boom, they're the same. Two colors central become unrecognizable as they lose their identity. Why do they lose their identity? They lose their identity because there always has to do with this color is relative to its adjacent color. So colors change, even though the physical color does not. It's perception. Are they the same or are they different? They're the same. Right? Because basically what's happening here, the reason that you might have thought this looked lighter is actually because of temperature. This is a more yellow tone, and this is in a cooler area, right? Cooler colors, the blues, and this is, the yellows are pulling out and making this a little bit dark. All right, here's another one, not a comparison, but this is just to really show examples. What is happening is really just how much red you mix with the yellow. By doing this in a gradation, it appears here that the yellow is way behind the red stripes and the yellow is on top of the, right? So this idea of transparent space is really just a question of mixing and perceptions. Moving forward, simultaneous contrast. So with temperatures, for example, that this appears darker now because it's next to something light, and this appears lighter than this band. So I'll just go back to look at it again. When you flip back and forth, you know that the color doesn't change, but it looks suddenly lighter, suddenly darker. Here's a similar one. This is a green. It's supposed to be green, not yellow. And then it's a similar thing happens here. One of the key things is that you see as the colors are more high key, meaning brighter, more chroma, that there's more contrast of the same color. So you see the purple against the green, purple against the green, it changes the contrast level. So these are strategies used for designers, for artists, and how you approach things. If you go up to a piano and just start like hitting keys, you're just going to get noise, right? But if you go up to a piano and you know how to play a piano and you hit, I don't know, 3 or 4 of the key that makes a chord, you're going to get a certain harmony, right? The same thing is true with color. The same thing is true with color, that it can be broken down into different, well, we're going to talk about that. There's the monads, the dyads, the triads, the tetrads, that it's basically how they are evenly spaced on the color wheel creates different harmonies. More color is not better color. Just like hitting more keys on the piano is not going to make a better song, right? It's about seeking out and searching for specific color harmonies that will do what you want it to do. This is just an example of a monad where you have, within a hue, you can have all the tints and shades, various tints and shades of a tone that's red will create one image. And that can be used in lots of different ways. This is sort of a similar thing where you can create volume and form, or you can create, this is a graphic design where you want to have a specific tone for this image, right? So you'll use a more monochromatic palette. This is another version of other artists that are using monochromatic, one color. Then you have analogous colors, which is another type of harmony where there are different ways of breaking them down. Generally, it's any 3 colors that are next to one another. This, for example, would be, in graphic design, an example of an analogous color scheme. Then you have this idea of the dyad, or what is also referred to as complementary colors, where you can put purples and yellows together, blues and oranges together, reds and greens together. Those are complementary colors. See a lot of New York teams like that orange and blue. This is another example of an actual artwork of Edward Hopper, where you see these really fantastic greens, and then these bright reds really make it dynamic. So then you have the triad. Triad can be a lot of different things. For example, the primary colors and secondary colors could fall into a triad, where you have 3 colors. You have people like Mondrian. This is the red, yellow, blue classic triad. This is what Mondrian used for the greater number of paintings that he's well known for. And then you have what's called a split complement, or a triad. It's another version of a triad where you can work with the complement, but you're not using the complement, you're using the colors that are adjacent to the complement. And this would be an example of that. So this is a very clear relationship of the green, the blue, and the orange. All right, so then there's the tetrad. This is where the chords go up from 2 to 3 to now 4, right, just like in music. The tetrad could be a lot of different things. This is where what we would call a double split complement. So it's the same thing as where basically you're dealing with complementary colors where the colors that are adjacent you're not using. And then here you have the hexad, where I think this is fun too because you see the relationship of tints and shades of those colors and how those work together. So that's when you might refer to in a painting the different tonality. You have other things that come up like temperature. You heard me talking about that a bunch of times already today. Warm and cool. But it's also what those things allude to: sky and water and shade versus sun and heat and fire, basic warmth. You see that happening by contrast in a lot of art, where Monet did multiple times at different times of the day and of the same cathedral. And here you see just two examples that are adjacent at different times of the day, different days, different temperatures. That also can happen in a place like interior design, right? Where the vibe, the feel of a room could be entirely different if it has a warmer space that you're creating with more reds and oranges and yellows versus something cooler. I mean, this might seem obvious, but it's also something that can be very, very strategic. So moving into more cultural, symbolic uses of color.